Hello and welcome back to Physics 123, Quantum Mechanics 1. We are still on the second chapter of this course, which is on the time-independent Schrödinger equation. So before we proceed with our today's lesson, let's first review what we have discussed so far. So we have derived the time-independent Schrödinger equation, which is also an eigenvalue equation. So we have derived the orthonormalization equations for the time-independent wave functions, psi n's, and we still normalize the wave function in the same way. The integral of the absolute value of psi squared dx, which is just the probability density. So this means that the probability should always, the total probability should always be equal to 1. So we also have defined that the true wave function, or the wave function at any time t, is just a linear combination of the time-independent wave functions, psi n's, where the cn's, the linear combination coefficients, can be obtained by using Fourier string. And these cn's actually represent the probability of finding the particle, or the probability that the particle is in the state psi n, or the probability that the particle has an energy En. And the average energy of a particle is basically just the weighted mean of all the possible energy values. And we will still use the expectation value formula, where if you want to find the expectation value of a physical quantity Q, we just sandwich it between the psi star and psi. Okay. So let's now proceed to our lesson, which will now be on the harmonic oscillator. So for this lesson, our U, the potential energy, will be that of the harmonic oscillator. So you actually have encountered this potential energy before in classical mechanics and in your basic physics. The potential energy of a spring, 1/2 kx squared. So let's now proceed with our lesson. So the harmonic oscillator potential energy is 1/2 kx squared, or in terms of the angular frequency, it's 1/2 m omega squared x squared, where m is the mass of the particle and omega is the angular frequency of oscillation, because this is an oscillating quantity. So if we plot this, it looks like a parabola due to the x squared term. So in classical mechanics, this corresponds to the energy of a spring, potential energy of a spring, or a marble trapped in a frictionless parabolic ball. So if you have in classical mechanics, you have a particle here moving up and down, up and down, up and down, endlessly, since we are considering a frictionless surface. So you will notice that in that case, half the time the particle has the maximum kinetic energy, and half the time it has, maximum potential energy, and when the particle is here, it has a maximum kinetic energy. So it's a beautiful example of the energy conversion from kinetic to potential energies. So using this potential energy, our time-independent Schrödinger equation now becomes this. So this is our U of psi. So there are two methods in solving this second-order differential equation. We can use an algebraic method or an analytical method. So for this lesson, we will just focus on the algebraic method. So in the algebraic method, we rewrite our Schrödinger equation such that it will look like or this is just our Hamiltonian here. We take out the differential the Hamiltonian operator. And if you will notice, this term negative h bar squared d squared over dx squared, this is just the quantum momentum operator form, p squared. So p squared m omega x squared of psi. So we want to find another form of our Hamiltonian here. And we can do that by something like taking the root of this term here. So we can actually write our Hamiltonian now in terms of these operators a plus and a minus, which we will call the ladder operators. So a plus, which is this one, negative ip plus m omega x, is the raising operator, and a minus, so you get the lower sign, so positive ip plus m omega x is the lowering operator. So if you multiply, for instance, a plus and a minus, so a plus is the upper sign, so negative ip, and a minus is the lower sign, so positive ip plus m omega x. So if you multiply a plus and a minus, you will get this. So just the square of this constant here, which is this one, and then the first term, so you have negative ip multiplied by positive ip, so you will get p squared. Again, negative I times positive I is negative I squared, which is equal to positive 1. And then you have the square of this, so m omega x squared. And then the cross term, so negative I m omega px, and then positive I m omega xp. So we will get this. Now, you may be wondering, why didn't I cancel this out, xp and px? So in quantum mechanics, we call this a commutation relation. So in this case, it's a commutation relation between x and p, and we usually write this as this, x and p. So in general, this is the commutation relation between variables a and, or quantities a and b. So this is ab minus ba, and this is not necessarily zero in quantum mechanics. Take note, in classical mechanics, this is just equal to 0, since this is the commutation relation, commutative. AB, if they are commutative, if a and b, if a commutes with b, this means that AB is just equal to BA. So in the realm of numbers, for instance, 3 times 2 is just equal to 2 times 3. Multiplication is commutative. Addition is also commutative. So 3 plus 2 is just equal to 2 plus 3. However, subtraction is not commutative. It's non-commutative. So this is the commutation relation between two variables or two physical quantities A and B. Now, in quantum mechanics, not all operators commute with each other. So meaning, actually, in the specific example of position and momentum, xp, the commutation relation of x and p, position and momentum, which is xp minus px, this is actually equal to I h bar. So it's not equal to 0. It's actually equal to I h bar. Now, of course, in the classical limit, h bar is a very small number. So in the classical limit, this is just approximately equal to 0. And position and momentum commute. So meaning, we will relate this to the uncertainty principle. So meaning you can, in classical mechanics, you can both measure position and momentum at the same time. But in the quantum realm, h bar is already a big deal. It's already a big number. It's no longer insignificant. So therefore, in quantum mechanics, you cannot measure position and momentum at the same time. So the consequence of this commutation relation is the uncertainty principle in position and momentum. So letting this equal to I h bar, so we will have I times I squared, so you will have m omega h bar. You multiply that with this constant, and a plus A minus will just be equal to this. Now, if you will notice, this term here is basically just kaninga term, our Hamiltonian. And this is how we derive this Hamiltonian in terms of the raising and lowering operators that we define. So this is actually just something like the square root of this term here. So we use algebra method. So of course you can also multiply a minus to a plus. So therefore you can have two definitions of the Hamiltonian operators in terms of the raising and lowering operators. You can use a plus, a minus plus 1/2, or you can also use a minus, a plus minus 1/2. So you have two options to choose from. So you will also notice that the commutation relation between the raising and the lowering operator, meaning a minus a plus minus a plus a minus, is not equal to 0. In fact, it's equal to 1 due to the 1/2 terms here. So this is the commutation relation between the ladder operators. So a minus a plus minus a plus a minus is actually equal to 1. So they do not commute with each other. So if you take the conjugate of the raising operator, you will get the lowering operator. So the conjugate of a plus, the complex conjugate of a plus is a minus. And similarly, if you get the complex conjugate of a minus, you will get a plus. So they are the complex conjugate of each other. So I think that's obvious here. Because if you replace I by negative I, you get the other operator. So this is the action of the raising operator. If you operate the raising operator on a time-independent wave function or a wave function psi n, you will actually raise the state. So that's why it's called a raising operator, because it raised the state. So from psi n to psi n plus 1. So if you act this on psi 2, it becomes psi 3. So you raise it to a higher state, or to an excited state. Of course, there's a constant here, square root of n plus 1. Similarly, for the lowering operator, if you act it on a wave function, it lowers the wave function by 1 state. So if you act this in psi 2, you will get psi 1. I'm just gonna segue here, since we are dealing with we have talked about complex conjugation here. Now, for the expectation value of any physical quantity Q, the Q is actually acting on psi first, but you can also let it act on psi star by just taking the complex conjugate of Q. So Q conjugate acting on psi, then conjugate. Based on this definition, if you add a plus and a minus, you will actually get the position x. So you can actually write the position operator in terms of the ladder operators. But again, this is only applicable. You can write x in terms of this if your particle is trapped in a harmonic oscillator potential. Take note, you do not use this form if the particle is trapped in another type of potential. So similarly, if you subtract the raising and the lowering operators, you will get the operator form of momentum. Okay, so let's focus now on the wave function. So what are the wave functions, psi n's, and the energy levels, E n's, of a particle trapped in a harmonic oscillator potential? So we know that the lowering operator lowers the state of the particle by 1. So meaning if you let the lowering operator act on the ground state of the particle, so here in the harmonic oscillator, our ground state is psi 0, unlike in the infinite square well potential where our ground state is psi 1, because in this case psi 0 is actually not equal to 0. It's not the trivial solution. It's not the trivial or the obvious wave function. So in this case, since this is now the lowest energy state, acting the lowering operator on the ground state must be equal to 0 because there's no more state to lower it to. So using the operator form of A minus, which is in terms of P and X, acting on psi naught. So we can now get rid of this constant here. We multiply both sides by square root of 2mh per omega, and our differential equation reduces to this. So this is just a very easy differential equation to solve. Just divide both sides by psi naught. So we'll have d psi naught over psi naught. To integrate that, the answer of that is ln. So you cross multiply dx, you will have x dx. You integrate that, and of course the integral of x dx is x squared over 2. So you use that one, and you can now solve for the ground state of a particle trapped in a harmonic oscillator potential. So if you let the Hamiltonian operator, in terms of the ladder operator, you can have two choices, as I have discussed before. If you let the Hamiltonian operator, in terms of the ladder operators, A plus A minus, on this ground state, you must get the energy of the ground state times the ground state. And this will give you the energy of the ground state, which is 1/2 h bar omega. Now, if you want to get psi 1, the first excited state, you just need to use the raising operator, A plus. So in general, if you want to get the nth state of a particle trapped in a harmonic oscillator potential, you use the raising operator n times. So if you want to get the ground state, you raise it 0 times, so you don't raise it. This is already the ground state. If you want to get the first excited state, so you raise it 1 time. So n is equal to 1. So basically from the ground state, you raise it, you get the first excited state, you raise it again, you get the second excited state, and so on. And the energy levels for a particle trapped in a harmonic oscillator potential is just this one, n plus 1/2 h bar omega. So you can notice that for n is equal to 0, the ground state, it's 1/2 h bar omega. So get this one. So in the analytic method, I will not actually be presenting the analytic method, but just the final result. So in the analytic method, you use the solution in terms of Hermite polynomials, where the Greek letter C here is given by, it's just a function of x. And these are just the first 5 Hermite polynomials. So I'm just presenting this method, but if you really want to learn this method, so try to read the textbook and other advanced textbooks. So let's now have an example. So first things first, find the first excited state of the harmonic oscillator, psi 1. So we use this formula. So for n is equal to 1, so this one, 1 over 1 square root of 1 factorial, then a plus psi naught. So basically it's just a plus psi naught. This is just 1. So the raising operator acting on the ground state. So this is the raising operator given by this one. We use the operator form of P, which is negative h bar over I ddx. So there's an I here, so the I cancels out. And we will let it act or operate on our ground state. This is our ground state. So using that one, this is just a first order differentiation. You will get this form. So some constant here, x e to the negative some constant x squared. So the properties of the states of a harmonic oscillator are similar to the states of a particle trapped in an infinite square well. They are stationary states. So they're pictures in a movie. So they are stationary states. A combination of them creates a moving state, which is the wave function at any time t. And they are alternatively even and odd. So this is our psi naught. So this is a symmetric or even function, because if you replace x by negative x, you get the same function. So it's even. But psi 1, the first excited state, there's an x here. If you replace x by negative x, you get the negative. So this is an odd function. So the psi n, similar with the wave functions of a particle trapped in an infinite square well potential, the psi n's, the stationary states, are alternatively even and odd. So of course, if you will get psi 2, you will get an even wave function. Then psi 3 is odd. So of course, yeah, this is just how to get psi 2. So of course, using that manner, using that formula, finding the higher energy states is actually quite difficult for a harmonic oscillator. So let's now try this second example. So find the expectation value of the potential energy of a particle in the end state of a harmonic oscillator. So there's a particle and it's in the end state, psi n. So what's the average value of the potential energy? So expectation value of potential energy, we sandwich it between psi star and psi. So since our sized wave function here, supposedly this is a summation, but it's only in the nth state. So meaning it's in this summation only one term, n, for n is equal to n, or n. So you have psi m e to the negative I ent over h bar. So the conjugate of that is e to the positive I. So I'm just gonna write this one here, write this down here. So this is this term is basically just psi n e to the positive I ent over h bar, and this term here is psi n e to the negative I ent over h bar. So the time components will cancel each other out. So these two terms will cancel each other out. E to the I, e to the negative I is e to the 0 or 1. So you will just get a psi n conjugate. Psi n conjugate psi n. So this one, psi n conjugate psi n. And of course, your U is your potential energy operator, 1/2 m omega squared x squared. And we can actually use the ladder operator form of position x, which we have presented before. So it's actually the addition of the raising and the lowering operator. And you square that one and you will get this value. So you will notice that in this this term here, it's actually 4 terms. You have a plus a plus. You act or you operate the raising operator twice, and then a minus, and a plus, a minus, and a minus, a plus. Take note, these two are not the same. A plus and a minus do not commute with each other. Okay, so this means that our integral will be converted into, we will have 4 integrals essentially. Okay. Now, for the first integral, say this integral, if we focus on this one, so you are actually applying the raising operator twice on psi n. So in the first application, hindi maklaro. So I'm gonna do this again. Somewhere here. Claro. So you are actually applying the raising operator twice on psi n. So upon the first application, a plus acting on psi n, you will get square root of n plus 1 psi n. Then you remove, you factor out square root of n plus 1, then you act again a plus on psi n, and you will get another square root of n plus 2. So you will get square root of n plus 1, square root of n plus 2, psi n plus 2. This should be n plus 1. So you raise it from psi n to n plus 1. And then you raise n plus 1 again. So you will get psi n plus 2. N plus 2. Okay, maklaro. Psi n plus 2. Okay. So the first integral is just you will have this square root of n plus 1 n plus 2 psi n plus 2 as I have shown here. This second integral, or this term in the second integral, will be reduced to square root of n, and this one. So this, you lower psi n twice, so you will get psi n minus 2 as the final state. For this term here, first you lower it a minus psi n, so it becomes psi n minus 1, and then you raise it again. So from psi n minus 1, you go back to psi n. So you go back to psi n in this operation. Similar with this. So you raise it first, so psi n plus 1, and then you lower it next. So n plus 1, you lower it 1, so you go back to psi n. Okay. So this integral will just be equal to n psi n, and this integral will just be equal to n plus 1 psi n. So we use the orthonormality condition of our wave functions, our stationary states. So you factor out the square root of n plus 1, square root of n plus 2 terms here, and you will get psi n conjugate psi n plus 2. So since the subscripts are not equal, so n, the subscript of the wave function is n, and here is n plus 2, so therefore this is 0. This will also be 0, but this will be equal to 1 with a factor of n, and then this will also be equal to 1, and you have a factor of n plus 1. So you have n plus n plus 1. So what's left in this whole integral here is n plus n plus 1. So, or you have 2n plus 1. N plus n plus 1 is 2n plus 1. And you further simplify it, you have 1/2 n plus 1/2 h bar omega, where n plus 1/2 h bar omega is our definition of En, the energy of the nth state of the harmonic oscillator. So this means that the energy, the average potential energy of a particle in the nth state of a harmonic oscillator is 1/2 the total energy of that, or 1/2 the energy of that state. So of course you try to find, I will leave this as for you to explore. If you try to find the expectation value of, or the average kinetic energy, you will also get 1/2 En. And if you get the total, the average energy of the particle in the nth state of a harmonic oscillator, so which is just the kinetic energy plus potential energy, so 1/2 En plus 1/2 En, you get En. So again, this means that the average energy of a particle in the nth state of a harmonic oscillator is definite, isa lang. So it's distinct. So for every one state, there's only one energy level. Similar with a particle trapped in an infinite square well potential. So distinct ang energy. Okay, last example. So this last example is similar to the last example in the previous lesson. So you're given a particle, but it's now trapped in a harmonic oscillator potential energy, and it starts in this state. So again, our initial wave function is now in terms of the time-independent wave functions of the harmonic oscillator, the ground state and the first excited state, psi 1. Take note again, for a harmonic oscillator, the ground state is psi 0. For the infinite square well, the ground state is psi 1. So you're asked again to normalize psi, the same problem. Find the wave function at any time t and the probability density. Find the expectation value of position and momentum, or the average position and momentum. And if you measure the energy of this particle, what are the possible values and what are their corresponding probabilities? So first problem, normalization. So we normalize the initial wave function. So the wave function remains normalized at all future times. Okay, so we get the conjugate of this. So since these are all real, so the conjugate is just itself. and then multiply it with itself. So basically square of this. So what's the square of this? You have a squared, you have 9 psi naught squared, you have 16 psi 1 squared, and then the middle terms. You have 12 psi naught psi 1, and then 12 psi 1 psi naught. Okay, so if you have this one, you have 4 integrals. So we invoke the orthonormality condition of the wave function. So this one is just equal to 1. This is also 1. This is 0 because the subscript are not the same. And this is also 0. And you will get a normalization constant of 1 over 5. So therefore, your normalized initial wave function is given by this. So you can already see here that C0, the linear combination coefficients, are already obvious. C0 is 3 over 5. C1 is 4 over 5, or 4/5. So when we now try to find the wave function at any time t, using the energy levels, ENs, so we already know it's now obvious. C0, the linear combination coefficient C0 is 3/5, C1 is 4/5, and the rest, C2, C3, C4, are all 0. So in this summation here, there are only two terms in this summation, n is equal to 0 and n is equal to 1. Or this summation is only from 0 to 1. So using the energy values, n plus 1/2 h bar omega, so E0 is 1/2 h bar omega, E1 is 1 plus 1/2 or 3/2 h bar omega. When it comes to the harmonic oscillator, I will not require you to expand the time-independent wave function, psi naught and psi 1, because that's very long. But again, this is only for the harmonic oscillator. If you try to if your particle is trapped in the infinite square well, I will require you to expand the it's just very short. It's just in terms of sign, mga psi n's for a particle in an infinite square well. Okay, so this will be your wave function at any time t. So you can check that at time is equal to 0, this will reduce to this one, or the normalized form of this initial wave function. So of course, if you square this, or you to get the probability density, it's just the conjugate of this multiplied by itself. So the conjugate of e to the negative I omega t over 2 is e to the positive I omega t over 2. So the conjugate of this term here is just 1 over 25. Sorry, the absolute value squared of this term here is just 1 over 25. And for the terms inside this bracket here, the absolute value squared of this term here is just this one. So 9 psi naught squared, 16 psi 1 squared, 24 psi naught psi 1 cosine omega t. Again, the cosine term is due to the addition of e to the I omega t and plus e to the negative I omega t, as we have experienced before or encountered before. So this is the probability density. So the probability density is dependent on time, and again, it is oscillating at an angular frequency of omega, similar to the frequency of oscillation of a particle in a harmonic oscillator na potential energy. So in finding the expectation value of position, again, you sandwich x, or you can take out x because this is just a multiplication operation, and multiply it to psi squared, or the probability density, which we have previously obtained. So the integral formulas that you will need here is the Gaussian integral formulas. So you will encounter integrals of this form. So x times psi naught squared, where psi naught squared is your ground state. So you need to use the ground state form, which we have obtained before, and also psi 1 in our first example, psi 1. For instance, I will just solve. You will actually have 3 integrals here. This integral, or integral due to this term here, multiplied by x, and integral due to the second term here, multiplied by x, and so on. So for instance, for the first integral, I will just demonstrate the first integral. So you will get something like for the first integral, there will be a factor of 9 over 25 integral of from 0 to a of x and then sine naught squared. So if we go back to our ground state, sorry, where is our ground state? I forgot to write the ground state. Okay, this is actually our ground state here. So this is the ground state squared, sine naught squared. So if you square this one, you will get a factor of m omega over pi h bar to the 1/4. So you square that to the 1/2, and then e to the negative m omega. So square of square of this exponential. So just multiply. So it now becomes h bar x squared. Okay, I'm just gonna use this in exponential form. E to the negative m omega over h bar x squared. Take note, the 2 here cancel out because we raise it to the power of 2 dx. So this is the first integral. So let's go back to the example number 3. Example number 3, letter C. Okay, so this is actually the first integral. Okay. Okay, sorry. The limit should the 0 to a limits for the infinite square root. It should be from negative infinity to positive infinity. Okay. So you use the Gaussian integral formula, but again, for this integral, actually, you don't need to integrate because this is an odd integrand and the limits are even. So if you have odd integrand, even limits, that's automatically 0. So the first integral actually corresponding to this is actually 0. So you do the same for the second integral and the third integrals, and you will get this result. So you will notice that the average position is oscillating with time, similar with the previous lesson. So the oscillation is the frequency of oscillation is omega, similar to the angular frequency of the harmonic oscillator, 1/2 m omega squared x squared. So again, if you find the average momentum, so you sandwich again the operator form of the momentum, or if your expectation value of x depends on time, you can just get its derivative and multiply by m, which is what we will do. But you can also use this formula. You will still get the same result. So doing that, taking the derivative of this, it's a cosine, so the derivative of cosine is negative sine. So a negative average means that most of the time the momentum is negative, or in the negative x direction, negative I hat or negative x hat direction. Letter D. So if you measure the energy of this particle, what values you might get and what probabilities. So we have already obtained the CNs, C0 and C1, and the CNs essentially gives you the probability that the energy of the particle is En. So since we only have two CNs, C0 and C1, then therefore there will only be two possible energies. So if you measure the energy of this particle, there are only two possible values, E0 and E1. So E0 is 1/2 h bar omega and E1 is 3/2 h bar omega. So the linear combination coefficient C0 is 3/5 and C1 is 4/5. So therefore, the probability C sub 0 squared is 9/25, or 36%. This is the probability that if you measure the energy of the particle, it's 1/2 h bar omega, or it's in the same way of saying as if you uh, determine the state of the particle, there is a 36% chance that you will find it in the ground state, or psi 0. And correspondingly, the probability that if you measure the energy of the particle, you will get the first excited state energy, or 3/2 h bar omega, is 64%. And the rest of the probabilities are 0. The probability that when you measure the energy of the particle, you will get, say, E3 or E4 or E5, it's not possible. So only two energy values are possible in this case, E0 and E1. So that's the end of this lesson on a particle trapped, a quantum particle trapped in a harmonic oscillator potential energy. So in the succeeding lessons, we will be talking about more realistic potential energies, and we'll also discuss about a free particle, a particle with no which is subject to no to no potential energies. So essentially it's free because it's not subjected, it's not trapped in any potential. So thank you for viewing the video, and I will see you again in the next lesson.